エッセンティア音楽家、エンジニア、ヨゴ・ユイチ様によるセッション、オーディオアプリケーションを Web で作るをお届けします。それではヨゴ様、よろしくお願いいたします。
お願いします。Hello, everybody. First of all, I'd like to say a big sorry to my fellow Japanese people for preparing this talk in English. But I actually prepared this talk in both English and Japanese. So this slide is actually fully localized for both languages. So if you want to follow along with my presentation on your mobile phone or something, now is the time to scan this code and you can see the Japanese version if you want to. And there's another thing I need to apologize, which is that I didn't know the theme that I'm using for this slide div had dark mode version and the non-dark mode version. And because my computer is in the dark mode, I prepared everything in the dark color. But this morning I realized that when it's not dark mode, it looks horrible. So yeah, sorry for that. Okay, anyways, and I just have to switch it back to English. And so making sound on web, as far as I know, there are two ways to make sound on web. One is to use HTML audio element, or you might call it the audio tag, and the other is to use Web Audio API. And so which one to choose? Well, I would say I think you should probably stick with the HTML audio element if your case is just to play a sound file and you don't need to control the loading or you don't need to, apply anything to the sound. You just want to play it just the way as the sound file is. In this case, I recommend you to just use HTML audio element. So it will look something like this. You just put the audio tag, and if you just put the controls attribute, you will get this kind of built-in controls by which you can just, play like this. And it will work 100%, like all the time, I guarantee. Well, I don't guarantee, the browser companies guarantee. But anyways, and if you wanted to do it imperatively, you can also use the audio element by calling the new audio constructor and passing the path to the sound file you desire to play. And you can just call the play method and you get the same result. Yeah. By the way, this is a sound that I made a few years back and I'm happy to share it with you guys. And so yeah, this is very successful in its own way, but maybe if you're not happy with what I just showed you, it's maybe your time to dive into the world of Web Audio API. But I'd like to ask you all, by a show of hands, how many of you here have ever used Web Audio API before, either directly or through some libraries like Tone.js? Don't hesitate. Yeah, 1, 2, 3, 4. Oh. Actually, a lot more than I expected, but okay, yeah, but not a lot. Anyways, so what's Web Audio API? It's the standard high-level JavaScript API. It's the only JavaScript API you can use to manipulate or produce or, anything with the audio-related things. You always go to Web Audio API. There's nothing else you can use in the world of web. And it works in all the browsers, by the way. And the unique feature of the Web Audio API is that its architecture is designed so that everything is like node-based graph kind of thing. As you can see in the diagram in the right, you can connect any node to one or more nodes at the same time. And they will run on a separate audio thread than the main thread where your Vue.js code or React code might live to run and do a lot of busy business. And also, Web Audio API comes with a lot of built-in audio nodes for common tasks, such as gain controlling or filtering or producing oscillator-based sounds or maybe analyzing some incoming sound signals or something like that. And here is a simple playback example that I created with Web Audio API. And wait, sorry, I just need to. Okay, so what you're hearing right now is purely coming out of Web Audio API, and this is not being produced by audio tag nor the audio element. And so on the left, I have a simplified explanation of what's going on here. So when you use the Web Audio API, what you first need to do is to create audio context. This is kind of similar to when you use WebGL, you need to create the context. This is essential for using Web Audio API. And sorry, I'm just gonna turn it a little bit. And because in this example, I'm using a sound file, I need to create a node called buffer source node, which is the built-in Web Audio API node for managing static sound file. And then just because I wanted to make this example a little bit more interesting, I actually put filter node in between the source node and the destination, which is the speaker. So when I play with this slider, sorry, oh, why is this so hard? Why is this so hard? Oh, no. But you heard, right? Yeah, it got a little bit muffled. Yeah, like this. This happens because I have filter node created here, and this is where the magic happens. You can call the .connect method on any Web Audio API node to connect to other node. So in this case, the source node is connected to the filter, and the filter's output is going to the destination, which is the speaker. So that's why this is happening. And also, if you forget to start the sound, it will also not produce any sound, and I fall into this trap like many times, but you need to start playing back the sound. Anyways. So yeah, so there I had basic playback functionality with some filter applied to it, but probably in most cases, this is still not probably enough for your business use cases because, it's still very limited. So that's where AudioWorklet comes to the rescue. So what's AudioWorklet? So AudioWorklet is basically allows you to write your own custom node in JavaScript. And it will run like just the same way as the other built-in web audio nodes on the audio rendering thread. And yeah, so there's no interference with the UI thread. And when you write your own custom audio worklet, you're required to write two scripts, one for the audio thread and the other for the main thread. And the main thread part of the code first needs to call a function called add module to load this processor script. And then you can instantiate your custom audio worklet node, and your audio worklet node and your audio worklet processor can talk to each other bidirectionally. And I'm just going to show you a simple example so that you can probably have a better understanding of what I'm talking about. So here, I have a side-by-side set of audio worklet. And on your left is what you have for your main thread, maybe where your Vue.js code might run. And on the right is where you use your worker thread to run this chunk of code in a separate dedicated thread. And this example is just a basic volume controlling processor. And all you need to do is to define a class that extends AudioWorklet processor. And you're required to implement a function called process, which gets inputs, outputs, and parameters. And as the argument's name suggests, inputs stands for something that comes into your node, and outputs stands for something that goes out of your outputs. So basically, if you don't do anything to the outputs, it will just pass through whatever was given to it. And because in this example, it's just trying to control the volume of the input signals, it's just writing a very simple for loop and multiplying a certain number to the input signals. Thus, you get the volume control. And once you have this kind of your own processor written, you can load your script in your main thread like this. You call the audio context.audioWorklet.add module, and now you can instantiate your worklet node like this, and then this will just behave like any other built-in audio web audio API nodes. So you can use .connect to connect to it, or you can call gain.connect to connect to something else. And here's another example that I wrote with web audio worklet. Okay, so this is just a simple snare sound that I found from somewhere, and right now this slider is set to dry 0%, so it's just playing the original sound as is. And as I drag this slider to the right, you'll start to hear some kind of reverberation in the sound. And so this is basically like a mix knob, like how much you want the original sound to be in the output signal. And below here, I think this determines how long the tail is. And actually you can also, you can also change the source sound to something else. Let's try this water drop sound. So this is the original sound. And you get something like this. So this is just a very boring, simple example, but what I wrote for this code is basically just the same thing as the game processor that I showed you earlier. The only difference is the process that I do here. I've kind of abbreviated a lot here, but basically, in the end, you will only need to manipulate the outputs arrays to get the altered signals. That's all I'm doing for here. And then after I created this processor node, I call add module, and then I instantiate the reverb node that I defined, and then I connected the reverb node to the speaker. Source node goes into the reverb, and reverb goes into the speaker. So that's what's happening. And when I change the slider, the UI thread called this reverb node .port.post message to send that the event that user has changed the parameters, and the reverb processor will receive this event like this, and you can register a callback to change the instance variable of the node. And there's one thing that I really think everybody should know about AudioWorklet is what I call the 3 millisecond rule, which is, so in most audio devices, the default sample rate is usually configured to be 44.1 kilohertz, which means that your process function will be called 344 times per second, with the inputs and outputs having the length of 128. So you need a lot of computation to do in a very, very small time span, which is actually 3 milliseconds. So that's what I mean by the 3 millisecond rule. And if your JavaScript code for the processor node, for some reason, does not make it in time for the 3 millisecond time span, it will start to cause some glitches in the output signals. And I actually have a live demo of artificially producing this kind of glitches. I managed to do this by writing a while loop like this, which does nothing until this certain time has passed. And this is a little bit the off topic, but I actually wrote this code and it worked pretty well when I was running in dev. But when I built the final version, the optimizer kicked in and took out the whole while loop because this while loop was not doing anything. So yeah, I kind of actually did some, not necessary thing in the while loop, but still I got the outcome. So this is just a very, very basic sine wave being produced in my processor. And what's shown on this on the top shows how much time it took in each process call. So right now, because I'm not adding any stress on the processor node, it's instantly pretty much executing each function call. But as I produce some artificial stress in the processor node, it will increase the average time it took for the process function to execute. And when it reaches the 3 millisecond, you start to hear the clicks. And when it's like way too much, it will just, not respond to it at all. So that's what I mean by the 3 millisecond rule. You always need to make sure that your process function will be executed under the 3 millisecond time span. So even though V8 is actually pretty fast, but still sometimes you need more speed. And that's WebAssembly comes into play. And leveraging WebAssembly for AudioWorklet has some pros and cons. And I'm just going to talk about the pros here, but it has nearly native performance for complex audio processing, of course. And you can reuse a lot of existing audio code bases in the browser, which are often written in C and C++. And I've only found 2 options for today, but I'm pretty sure there are more. But the first one, JUCE is a very, very widely known framework in the audio development world. It's something like React in the world of web. Sorry, Vue, of course, Vue. Or Next. So it's a very big framework written in C++. And it's used by Adobe, Steinberg, Universal Audio. They're very famous companies in the audio world. And it's cross-platform, and it supports a lot of plugin formats. And there's a guy who managed to convert JUCE to WebAssembly, and I found the demo running on web, which looks like this. To be honest, I'm not really a big JUCE user, so I don't really know what these are. But sorry, it's so loud. But yeah, this code is originally was originally written by C++ and was meant to be run in standalone applications. And now it's running on the web. So this is one thing. The other thing is my favorite, which is to use Max. And what's Max? Max is a visual programming environment for audio and multimedia, which looks like this in the picture. And you can connect objects with cables instead of writing codes. And you can build a lot of synthesizers, effects, and more. And Max very recently shipped a feature called Rainbow, RNBO, that exports Max patches to WebAssembly. So I actually have a project that I did with Kentaro, who is the chief sound designer at Team Lab. And I'm happy to share this with you. And yeah, and you can also record, and you can play back, and you can also, you can also, let's put this water again to here, and you will get something like this. It's so fun. Yeah, I recommend you all try this. This is also included in the presentation. So, and if you put something like this music, for example, this will. Yeah, this feels so good. So anyways, so this guy made this insane DSP, the audio processing. So our collaboration was like, Kentaro designed the audio processing part in Max, and he exported the patch to WebAssembly. And then I built the UI with Svelte and integrated the WASM module. Yeah, Svelte. And connected the UI control to the parameters. And then, yeah, that's what you heard. And lastly, I would like to share a very, very experimental thing that I recently tried. And to be honest, I completely wrote this by vibe coding. So I totally do not understand what's going on, but it still works. Because, I mean, in theory, I know what WebGPU is, and I know what WebAssembly is, and why not just put them together? Because, sometimes some certain audio processing requires massive parallel processing to do, and WebGPU is a perfect suit for that. And so here's what ChatGPT originally gave me, and I revised it with Cloud Code last night, and which sounds like this. So this is the original signal. And as I increase this wet mix, you hear very rich reverb. Although it has some distortion in it, which is not intentional, but it still produced very intense outcome, which is probably very, very heavy if you were to do it on your CPU, because it requires 3.9 billion operations per second for 3 seconds of reverb. And that's why I say GPU is the perfect fit for this kind of operation. And yeah, so that's pretty much it for me. And so I put this self-introduction at the very end, because I thought everybody is probably listening to the other session right now, the debate, and I wanted to do my self-introduction in the end, so that's why it's coming right now. So who the hell am I? I'm Yuichi Yogo, and I studied composition of music at Tokyo University of the Arts, aka Tokyo Geidai in Japanese. And I also run a company called Escentier, and we make video production, 3D graphics, and music, sound design, as well as web apps and games and other digital products. And that's pretty much why I'm kind of familiar with the very minor API that exists on the web world. And lastly, is there Anthony here? Okay, yeah, Anthony. I would like to give special thanks to Anthony Fu, who is a friend of mine via our mutual hobby bouldering and creator of SlideDiv. And this presentation is powered by SlideDiv. I think, as far as I know, it's the only tool that makes sounds and enables localization. So I actually have 5 more minutes, but okay. Can I just end early, or do I take questions? Okay, thank you.